moment as we get ready for the next speech, which is our last deep dive technical talk of the day before the CTF announcement. So the moment we've all been waiting for is almost here. Now, before I invite the next speaker on stage, I want you to know this talk is also inspired by some fantastic Tolkien works. So the next talk is about Lady or Lord of the Ring Zero. This is a deep dive technical talk. After that, we're going to have our CTF announcements. Now, let me know if you had the chance to meet our sponsors. Did you get swag? Did you get food? Did you get stickers? Anybody want some more stickers? Too bad, I'm out. Should have been here earlier. All right, so this next speaker, his name is Ido. Let me tell you something. We had a whole bunch of different speakers backstage today. This guy is ice cold. He's the coolest speaker we had. Everybody else was nervous, excited. Not this guy. He knows his stuff. Please help me welcome him to the stage, Ido Veltzman. Ido.
Thank you.
Come right here and smile for the camera right there. Yeah. So Ido is going to talk to us about being a lady or a lord, take your pick, of the Ring Zero. And he's going to be going deep into all of that stuff. He's got experience with kernel development. He's got experience with reverse engineering, with OS internals. What do you do on your free time, Ido?
Going to the gym, playing drums.
Release code on GitHub.
Release code
on GitHub. Play drums, as one does. Okay, you got everything you need, Ido?
Yes, sir.
Everybody here ready? Last technical deep dive of the day until the CTF announcement. Let's hear it for Ido. Let him know you're still here. Oh, yeah. All right. Let's go.
There we go. So first of all, thank BSides for having me here. Thank you all for staying. And let's start. So my name is Ido. I'm doing open source on GitHub, and doing some projects related to evasion, related to kernel development, related to injection methods. I'm posting it here. There's also a QR code here for you to follow along. We will also have code snippets, but besides that, if anyone wants to look at the code of the driver I'm going to use Nidog, which is my open source rootkit, and I will use it for the demo today. I'm also posting blogs in this URL about my projects, about kernel development, and the blog post Lord of the Ring Zero is what inspired today's talk. So what we're going to have today is we're going to learn how to hide our user mode and malware and artifacts. We are going to talk about anti-detection, about unregistering callbacks, about disabling ETWTI, about IRP hooking, what is IRP. We're going to talk a little about PatchGuard and DSE and how can we bypass them, and some tips about safe kernel development, and a little bit puns on the side. So let's start. So first of all, what is a kernel callback? And sorry, we're going to talk in this section about what is a kernel callback, how EDRs and antiviruses are using kernel callbacks, and how it can be used from an offensive point of view and defensive point of view. So first of all, what is a kernel callback? So kernel callback is a mechanism that provides a general way for drivers to get information about events that happen. In the end, if, for example, you want to access some file and you don't have permissions to, some driver needs to handle it and give you the access denied you're all used to get. And if you're trying to create some process, and this is, for example, Mimikatz, a very known bad process, some antivirus will want to inspect it. So how they're doing it is via callbacks. And all the callbacks the operating system knows to call the callbacks from a callback list, which is there, they are stored. So in that callback list, there's just a list of all the addresses of the functions that the operating system needs to run and call and execute them one by one. So we're going to talk about three different types of callbacks today. The first one will be object callback. Object callback is the callback that is registered for every event of pre or post operation. For example, if you want to open and handle to a process, you can call back, if a driver registered one, and callback of pre-open process will be called. We can see here an example of registering that kind of callback. Two callbacks, actually. One for a pre-open process and the other one for pre-open thread. And we're registering with OB register callbacks with our registration handle, and we're going to get a registration handle with our altitude, which is a unique identifier for each driver that wants to register a callback. So this is the example of the pre-open process callback, which I use on my driver NIDOG. This code is written on C++. And what we're having here is I wanted to protect my malicious process from being dumped or accessed by antivirus. So I'm checking if someone wants to access my process, and if it does, I'm just removing the permissions for closing that process, terminating that process, dumping that process memory, reading that process memory all along, and just returning the strict handle. So it basically, if it wanted to terminate me, it can do it anymore. We have a lot of types of callbacks. We have callback type for key operation. We have type for files. We have for events, for processes, threads, tokens. Not all of them are enabled by default, but we can enable them. We will see later on why we can't really turn them on. Every callback consists of this structure, which is the object type. It contains the type list, which is just a linked list to all the other object types. We have the name of the callback. We have the lock that we can use to make sure that no one else is using and iterating that object type. We have the callback list, and we have also other members that we won't discuss about today. But one picture is worth 1,000 words, and a demo was worth even more. So I'm having here a presentation of the pre-open process callback. So here we can see that I'm having two shells. I have the right shell that I'm using to activate and use my driver, and the left shell that is system. We can see that I have a process named Notepad, and I want to protect it. Let's assume this is Mimikatz. This is some process I want to protect. I don't want antiviruses to scan it. I don't want anyone to dump it. Here I edit it, and I show that I'm, in fact, system, and trying to kill it, but I can't. I get access denied. And when I remove that process from the list, we can see that once again, I will be able to kill it. So here it is right now, trying to do task kill, and in a second, it is done. We also have another type, notify routines. I think that every red team member in the crowd already heard so much about it, but I don't know how many of you actually dug into it. So let's do it today. So notify routines are three types of routines. We have the create process, that we say that what it does is we can get every every operation of creating process or terminating process. We have one also for threads, and we have one for image loading. We don't have any one for image unloading, just image loading. So here we also have a little demo. Here I didn't use NIDOG, I used the driver of my own. What I'm doing here is just the driver denies the opening of a process called Notepad. But if we are antivirus, we can do it not for Notepad, but for known bad processes that many threat actors are using, and it can be helpful. We can also use it not only just to block the creation of a process, but we can do it also for example, if we want to examine process when it is created and search for any type of a malicious shellcode or any other thing that can point that this process is illegitimate. The last type of callback is a registry callback. Registry callback happens every time there's a registry operation. So how we can register it is by giving the function that will handle these registry operations. We can give it altitude, which, like we said, is the driver's unique identifier, and we can give it we can give it context. We will get context, sorry, and we will get also cookie, which we can use later to unregister that callback. So this is the function that handles all the registry operations in my driver, which I chose to handle pre-delete key, pre-delete value, setting value, querying value. Anyone can guess what can we use for, I don't know, for query value? No one. Okay. So we can use it, for example, if someone wants to iterate or check if some value exists. A very common registry key for red teams and threat actors is the run key, which all know and love or hate, depends on your side. And what we can do is still put our malware there, but hide it, and that everyone that wants to query that value and check if there's something under the run key, we can just hide our malware from there. And this is exactly what this function does. So this function is checking if the caller is, if someone wants to do operation on a user mode object, and if it does, it continues. We're getting the registry key name and then the registry value and doing some validations to make sure we're not crashing the computer. And then we're trying to find it on some list that I defined and that you can add your registry keys, your registry values to there, and just protect your item. For example, in this case, the value. And we can see that if we find that item on that list, we're returning status not found. This is another demo. As we can see, we have here under our run key, we have Gandalf saying, "Fly, you fools." And let's assume this isn't Gandalf, this is a malicious one, and we want to hide it from the user. So as we can see, I hid it, and then it's no longer there. We can no longer see it, but once I restore it, we can see it once again. We saw that callbacks gives a lot of information. We're getting information about, for example, processes, registry, threads, loading DLLs. We're getting tons of information that we, as malware developers this time, won't want this information to exist. So what can we do? how can we find this callback and unregister it and just blind that spot of anti-malware vendors. We're going to talk about this today, right now, and we will also have some nice demo of unregistering the WD filter driver, which is the Windows Defender's filter driver. Like we said earlier, callback, all the callbacks are stored within the callback list. So it means that what we can do is just iterate that list and find if the callback that we want to unregister matches the image base of the kernel driver that we want to remove. So let's say we want to remove the callback of Windows Defender. What can we do? What we can do is listing all the callbacks, finding the callback that we want, and connecting it to Windows Defender by finding the image base of Windows Defender and see that it matches. So this is the demo. For the demo, I chose OB callbacks. We can see here that I'm querying all the pre-opening handle for processes. We can see the value of WD filter here, and here we are removing it with little lags. And after we will remove it, we see that it was replaced with another callback pointing to my driver. That callback does essentially nothing, and because the callback of WD filter driver will never be called, all the detections that relies on that callback will also never be fired. But this isn't all. In the kernel, we can do lots of stuff. Not only callbacks. What else we can do? Well, we can use also another thing called ETWTI, which, let's go a little bit back and explain what is ETW. So ETW is a mechanism that Windows provides us to log and to trace all kinds of events that happens on the operating system, whether this is user logon, whether this is some application that ran, or something that crashed. But what is ETWTI? Well, ETW consists of providers. Each provider is responsible for handling and logging the information for that provider. For example, there's a provider that's called ETWTI, or ETW Threat Intelligence, that its whole purpose is to log events related to security. So if there is some interesting stuff like remote writing to virtual memory, this can imply on something bad. Or remote queuing APC, which is a very common method to inject shellcode. ETWTI can give you that information and help the defenders to get more insights, create more detections, and deny the execution of the malware. So how can we disable it? Each provider is made out of this struct, the ETW reg entry. It contains within it the ETW GUID entry that contains within it the trace enable info. And in this trace enable info, there is a little value here called isEnable. So what we can do is just zero it, and everything that uses that provider won't be able to use it because it's seemingly disabled. How we can do it for real and not just flashing lights, and I want to show some code. So this is the code that can be used. How we can do it is by choosing some function that is close to that provider object that we want to get. And then, oh great. And then we can use a signature that we found of that object and search it within the kernel near that function to find it, find the struct of the enable information, and just copy the value 0 to is enabled if we want to 0 it. Or if we want to restore it, we can copy the original value. Let's talk about the other thing here. IRP hooking. So there's a lot of information, and I hope that, and if you want, this presentation will be published, so don't worry. So IRP hooking is, let's talk about something previously, which is the driver object. Driver object is the object that represents each driver on the kernel. It contains the initialization function, the unloading function, the device object, and also something called major function. Major function, as you can see, this is an array of some IRP functions. But what is IRP? IRP is the standard of communicating from the user mode to the kernel, to a specific driver, and from driver to speak with another driver. So that packet is made out of two parts: the header, which is that stores some information of the original request, and the stack location that contains the juicy stuff, the user mode system buffer. There we can provide information, the IOCTL, if you heard about it, which is some code that is used for the device I/O control, which is a way to communicate with the driver. So like we said, there is some functions here in the major function array, that each function here should handle a different IRP. How we can use it? We can use it for our advantage to hook it. We can replace it with our malicious IRP handler to handle that function and run some code that we want with the data that the user or other drivers provided to us. A very common IRP hooks are hooking of the device control, which is used to communicate with the driver, IRP-MG write, IRP-MG read. MG stands for major, like the major function that we saw earlier, and IRP-MG directory for NTFS to hide some directories and some data. And what I will show you today is how we can hide a file. Not hide, but block access to. As we can see, there is a file here called Sauron, and we want to, let's assume this is our malicious file, and we want to block access to. Sorry. So what we can do is use our driver to add it to the list and try to delete it with a system shell. And after we are failing, we can remove it from the list, and you know the drill, it will be deleted. That's nice and all. We can do a lot of stuff from the kernel, and this is just the tip of the iceberg. So who's stopping us? What is stopping us from doing a complete havoc, cause a complete havoc in the kernel? Well, there's PatchGuard and DSC. Each of them is supposed to give protection on other aspects of the kernel. So PatchGuard, or kernel patch protection, is a mechanism that was introduced on Windows XP for a 64-bit only. It is meant to protect critical structures on the kernel. How it does it is by just crashing the whole system. Is doing kamikaze with a error code 0 hex 109. It is initialized on boot and is ran in random time intervals. Just to see what it does, for example, we can see the object type, which if we remember, we saw it earlier here. So, like I said, we can't really enable a file object type callback because the kernel eventually, PatchGuard, will detect it and crash the system, and we don't want it. We also see here IRP allocator modification, which is just the file protection I showed earlier. And like we saw, we can't really use it because, again, PatchGuard will detect it and will crash the system. We don't really like PatchGuard. So what can we do with it? What we can do with it is this is one way to disable PatchGuard. And this is what I will show today. Of course, there are many more ways, some better, some less. So in this way, we are loading a bootkit that hooks a specific function that is called right after the operating system is loaded, but not yet run, so we can modify it. Nothing protects it. So we can modify it and find the Windows kernel base, find the functions that initialize PatchGuard, and just patch the PatchGuard. Another thing, so, okay, we can somehow still do very damaging stuff, regardless of PatchGuard. We can register callbacks, we can basically dominate the user mode, and sometimes also things in the kernel mode, like the unregistering callbacks I showed earlier. So what is stopping us from actually doing that? Well, there's another mitigation called DC. DC is also introduced in Windows XP for 64 bits. It's meant to prevent drivers from being loaded in the first place. Unsigned drivers, of course. The signature is not your normal executable signature. You need a special signature from Microsoft for that. It is initialized by the Windows Boot Manager and triggered by driver loading. However, we can patch it. We can patch it by getting the CI DLL base address, which is the code integrity base address, getting the CI initialize address, which is a function that contains a very special object called CI options, and then just patch it and marking DC as disabled. So we can load our driver. And this is a very common method that is used widely, especially nowadays, on bring your own vulnerable driver attacks, to load another driver. Okay, we talked a little bit about the DC patching, the PatchGuard, the kernel from offensive side of view, from defensive side of view. Let's talk it about from the programmatic side of view. So in here, I want to note several things. The first thing when you write a driver is to never trust the user mode data. Always assume it's tainted. Maybe this is some user that don't want to do any harm. Maybe this is a malicious user. So take that in mind. Check the length of what you're getting. Check the destruct that you're getting if you're getting a struct. is exactly what you want. And if it is a struct, not only check that this is the struct that you want, check also its members. Because if people will only even do that thing, that little thing, so many vulnerabilities could have been prevented. Remember to always use logs. Logs are important. They are there for a reason. So make sure to use them to prevent all kind of time of access, time of use, vulnerabilities, race conditions, and so on. And where you're accessing usable data, make sure to use these functions, probe for read and probe for write. What it does is make sure that you can actually access that area and not crashing the system by accessing that location. But you will need to do some address check before that to make sure this is within that range, because probe for read and probe for write is examining the area. And if you know that you have a potentially dangerous code, you are doing some mem copy, you're from user mode buffer, use, try, and accept. You have it. All you have to do is use it. If it isn't some critical problem, you can catch that exception and handle it by yourself. So we got a little faster to the end of the talk. I wanted to give some time for questions, but a little bit before that, let's summarize what we had today. So we learned some different ways to hide our user mode malware and artifacts. We learned how to unregister and how unregistering callbacks work. We learned how to disable ETWTI. We learned what is IRP and IRP hooking. We learned the very basic of the basic kernel mitigations. We got some safe kernel development tips, and we enjoyed some pictures. So before I saying the summary for that talk, any questions? Yes.
Well, I don't have a microphone, but I saw this concept a bit with game protectors, that they're trying to hide a client. Like, for example, if you're trying to hack a game, then it would hide it from debuggers, from stuff like that, cheat engines, stuff like that. So, did you, like, is it always possible to deprotect some stuff using these techniques?
Well, so the question is that game cheaters often use drivers to manipulate the anti-cheat mechanisms, and is this always an option? Well, it depends on what you're doing. If you're doing game cheating, I'm not doing game cheating, but if you are, the race there and the armed race is very different, because the anti-cheat mechanisms can focus on very specific things, and so it has some capabilities that usually the antivirus and EDR industries are getting a bit later. So will it work on another driver of anti-cheat? I don't know, but I'm assuming that it won't work. In the end, this is an armed race, and the information security is doing, because of its nature, is doing things a little bit later. This isn't a new thing, but it is an old new, because it got some attention right now in the past few months, years, and yeah. Is there any other questions? Okay, so we have...
Right. Thank you. Aha! One simply does not say thank you without a meme. Well
That's
done.
right.
And I like it that you mixed Lord of the Rings
Oh, yeah, of
with
course.
Sorry, thank you so much. For a moment, I wanted to say Game of Thrones, but that's a different episode.
Ah, yeah.
Yeah, I was just confused. It's okay, it happens. It's a long day. All right, thank you so much, Ido, for being with us. I hope you all learned a lot of lessons from Ido. Let's smile to the camera right here, Shlomi. All right. Now, Ido, we have a small gift for you, token of our appreciation.
Thank you.
Go on over there. Now,